Hello everyone, welcome back to MAT052. This week I'm going to go over confidence intervals and hypothesis testing for the difference between two means. We'll just look at a piece of it. We won't go through the full setup for hypothesis tests, and we'll just do the test statistics. But this will kind of get us used to working with data and which way do we go when we're talking about confidence intervals and a hypothesis test for the difference between two means. Okay, so what we have to worry about is when we're doing with this is if we're dealing with data that is paired or unpaired. Okay, so frequently we will need to determine if there's any difference between the population mean of two data sets. So what we're going to be looking at is if we do some type of treatment and we may have two different groups. One of them is given the treatment, one's placebo, and we want to see maybe blood pressure, if there's differences between the blood pressure of the two. We can also be doing that as here's an individual, we're doing the same kind of blood pressure medicine maybe, and we're going to do it to the same group of people, but they may do it 6 months with a particular medicine. We'll measure blood pressures, and then the same group of people, after that one, they come back and they will do a different medicine. And from those same people, we're going to try to determine if there was any differences in blood pressures between the two medicines. That last example is an example of paired data where they're tightly coupled. One of the signatures of paired data is that there will always be the same sample size between the two. It's kind of the same people or the same kind of experiment between the two. And when we're doing unpaired data, it could possibly be two different data sizes. Okay, so unpaired data may or may not have the same sample size, but the data sets, areas usually from two groups. Treatment, for example, some people are given a treatment versus those that are given a placebo. Data sets are from two distinct areas, like North Carolina and South Carolina. Is there a difference between the mean age between people in North Carolina versus South Carolina, the mean weight, the mean height? So two different areas where they're not going to be the same people, and they may have two different sample sizes. So paired data usually consists of the same people or groups before or after treatment, and they are required to have the same number of samples in both data sets. We're going to see later why that's got to be true. So for the difference of two means, I want to know if the mean height between two different groups are different. Okay, it's kind of an example. So two samples are independent if the observations in one sample do not influence the observations in the other. We can test hypotheses about the difference between two population means. That test statistic, what we're going to use to test against if we're doing hypothesis testing, has a student's t-distribution. The number of degrees of freedom can be taken to be one less than the smaller sample size. So we'll look at both the sample sizes. They can be different in unpaired data, and we're going to use the degrees of freedom as pick the smallest one. We're going to do n-1 from the smallest one. Now, if we look at like a calculator or technology, when they do it, they do a little different method of calculating the degrees of freedom. But for us, that's what we're going to do when we're working by hand. So that's the more complicated formula used by technology, provides a greater number of degrees of freedom. It's just a little better version of it. And the assumptions that are necessary for one sample test must hold for both populations. Greater than or equal to 30, or we assume that both populations are normal. This thing that we're going to do is called the Welch's method. Okay. So let's start out with the confidence intervals for the difference of two means, independent samples. Degrees of freedom that we're going to use when we're calculating is just a smaller of n1 minus 1 or n2 minus 1. And then when we calculate that confidence interval, we're going to use this formula, and basically it is just saying x1 minus x2 bar. Those are the differences of those two means, plus or minus the margin of error And this is going to be a T alpha over 2. This is the critical value, and then we're going to do a margin of error formula for this. And that is just going to be that square root S1 squared over N1 plus S2 squared over N2. And that's our margin of error. So let's kind of take a look at this and see what we come up with using this formula. And we're going to calculate and interpret a 95% confidence interval. And I want you to notice that they say degrees of freedom. If you look for, it's like, let me go over here. There's the Z sample T interval. Here's the confidence interval between 9.8059 to 12.998. Here they're using a degrees of freedom 113. We're going to do that a little differently. So we've got, I'm just going to use their X1 bar. That's going to be 49.81472. Our X2 bar would be 38.41269. My S1, which corresponds to this, it says S sub X1, but that's what that is 3.69057. And then our S2 is just 5.89. Almost misread it. 5.89133. So we need to do a T alpha over 2. And since this is a 95% confidence interval, this is going to be T 0.05, so the C is equal to 0.95, and 1 minus C is my alpha, which is 0.05. That's my alpha. And then alpha over 2 is 0.05 over 2, which is 0.025. So here, 0.025, and my degrees of freedom, I like writing this down as a group because I need two things for the T, and that's going to be the smaller of N1 and N2. So N1 was 85, and my N2 was 71. So I'm going to use the degrees of freedom. The smallest one of these was 71 minus 1, which is my 70. Okay, so if I go back, I want to go back here just for a second. Let's see, if I go here, and if I run my A.3 table, this is a T. So hopefully I can get in here pretty quick. So I'm looking for 0.025. The area in the right tail is the one I'm going to use. So both sides are 0.025. That's that. And my degrees of freedom are 70. So this is my column 1, 2, 3, 4, 5. So if I go down and look for 70, what happens is that 70 goes between 60 and 80. And I'm going to use the smaller of those as the 60. 1, 2, 3, 4, 5. That's the column I was looking at. So this value is just 2.0. Okay, so I'm going to go back to my slides. We're going to work through there. That's where I did the DS60 2.0. What is the point estimate? Remember, for confidence intervals, I'm always building some interval on the number line. The number that starts between here is going to be X1 bar minus X2 bar. And I want to keep these in order to make sure that everything corresponds to what we're working with. Okay, so this is just going to be the 49.81472 minus 38.41269. See where I do the first one minus the second one. Everything I correspond just like it tells me to do up here, the X1 bar minus the X2 bar. And I'm going to run that through the calculator real quick. 3.81472 my minus 38.41269. If I do that, I get 11.40203. I'm going to carry out as many decimal places while I'm doing all my calculations as I can. And then at the very end, I'll round. Okay, so now my margin of error, this is the x1 bar minus my x2 bar, and then my margin of error is just going to be my critical value, T alpha over 2, times my standard error, S1 squared over N1 plus S2 squared over N2. 2, that's that 2.0 from there. And then I just need to put everything in. 3.69057 squared over my N1, which is 85, plus my S2 was 5.89133. I need to square that over my N2 of 71. And let's see if we can work that out. So I'm going to do this on my calculator. 2 times second, I'm going to use the square root function. 3.69057 squared divided by 85 plus my 5.89133 squared divided by my 71, and all of that up. .69057, and I get this being 1.611. Let's go with 4 decimal places is 113. Okay. So if I move up, I'm going to take this value, my x1 minus my x2, subtract this. So my 11.40203 minus, and this was like 10925. So I'm just going to recopy that number down and subtract. That gives me 3 decimal places, 9.791, less than my mean, and then I'm going to add this number to that one. That's my plus the margin of error. Okay, from what I do up here, this is going to be the plus. And then I get 13.0133. And now if I go back up to my slides, and they got a 9.8059 less than mu, less than 12.998. And again, what is the difference between this? Is they're using degrees of freedom of 113.27. It's our table only goes, we would have to work in between those things, but through technology, they can work this out and get a better value for T alpha over 2, and it makes this do a little different. But that's pretty close from what we're looking for. Okay, so that is the confidence intervals. Let's continue on. What about if we want to do a test statistic? I'll give you just a second on that while I'm working through. So the test statistic for the difference between two means independent samples, and this is the test statistic. The standard error down here looks just like what we have worked with, so we will be able to do here. Now here it's got minus mu1 minus mu2. This is your claim from H0. This is the value from the differences of the two means. So usually this piece is going to be 0. So I'm going to go ahead and work this all through and kind of give you an idea. The t value, the t-test statistic, so I'm going to compare this. If I go in just a minute, and if I do a test, I want to compare, here's my rejection regions like we did before, fail to reject, and this is going to be critical values based on the t. T's go with T's, z-test statistics go with z critical values. So x1 bar minus x2 bar minus mu1 minus mu2. So this is the hypothesized or the claim value. I'm going to slide that down for you just a second. So that's from the claim, and usually this thing is going to be 0. So you're claiming that there's some differences between the two or no differences. So then we have the very same thing, S1 squared over N1 plus S2 squared over N2. And again, this is based on, we're going to test against some claim hypothesis, H0, H1, and how we do that is to go sample. And these are going to be two different samples. We're going to get the values for x1 bar, x2 bar, and then this is how it tells us how far away from this one, basically saying, now it's 0 once we do this thing, but it's basically saying how far are you away from that claim, mu1 minus mu2. So we go back. So the mummy's curse. King Tut was an ancient Egyptian ruler. I'm sure you all have heard of King Tut, whose tomb was discovered and opened in 1923. Legend has it that the archaeologists who opened the tomb were subject to a mummy's curse, which would shorten their lifespans. A team of scientists conducted an investigation of the mummy's curse. They reported that the 25 people exposed to the curse had a mean lifespan of 70 years, with a standard deviation of 12.4, while a sample of 11 Westerners in Egypt at the time who were not exposed to the curse had a mean lifespan of 75 years, with a standard deviation of 13.6. I can assume that the populations are approximately normal, so that our sample size are not bigger than 30. So we need this extra condition. Can you conclude that the mean lifespan of those exposed to the mummy's curse is less than the mean of those not exposed? Okay, so what we're going to do is basically say, let's set up some things. The mu1 are the mean average of those exposed. Okay, and what we're going to say, so mu2 is normal. And what we want to do, can you conclude that the mean lifespan of those exposed to the mummy's curse, this one, is less? So this is less than mu2 in all of what we're doing. Okay, so the way I like to do it, here's our claim. We're going to do a complement. It's just the other stuff. So it could be this might be that one, or it could possibly be the condition that this is greater than or equal to. Alex likes to do this as less than versus equal to, but I like all of this because once you do the equals, you take care of all the greater than as well. We assign H0 and H1. That's our next step in hypothesis testing. We determine that the testing that we're going to do is from H1 that points to the left. So it's a left-tailed test. So if we did kind of a region, we can do that right now. Kind of set this up. There's our left-tailed test. Here's our fail to reject region here. Here's our rejection region. And since this is one tail, that area in there is the full alpha. And we're going to test this at the 0.05 level. Okay, so this automatically says I need something that separates this thing. And this is the critical value that separates regions. And it always matches whatever the test statistic is. If this is a T, that's got to be a T alpha from here. And that's what we're going to do. So we need a T alpha at degrees of freedom, the smaller of N1 and N2. N1 was 25, N2 was 11, X1 bar was 70, with S1 being 12.4. My X2 bar was 75, and S2 was 13.6. So this was the smaller, so this was 0.05, the full alpha because it's one tail, and then our degrees of freedom would be 10. So if I go back over, I'll go switch back over. I think I had this right here. I'm going to go back. Pull this up. So even though this is a right tail, this is going to be symmetric. So one with the right tail of this would be the very same value, it's just a negative number. So I'm going to go 0.5 with 10. 0.05 is my fourth down here at 10. So this is going to be 1.812. If I'm going to do that by regions. So now we're going to finish. Back over. So here's our test statistic. So we're going to do this T. Our X1 bar, 70 minus 75. And this is basically, if we're saying this is going to be mu1 greater than or equal to mu2, the differences, if I subtracted both, is basically 0. So I'm going to put a 0 there. And that's the way it usually works out, that, like I said up here, this thing is usually 0. So then divided by my S1 squared, 12.4 squared, over N1, which is 25, plus my S2 squared, 13.6, squared over my N2, which is 11. And if I do that on my calculator, give me a second. Make sure I do everything at the top in parentheses, 70 minus 75, divided by second square root, and then everything in there. The 12.4 squared divided by 25 plus 13.6 squared divided by 11, and that takes care of all of that. And then that would be a t-score of negative 1.0434, stopping there. And I'm going to plot this. So once I have this and all my regions set up, I'm going to take this and move it right up here. So again, this is the 0. This is negative, so this is, sorry, I was supposed to use a negative here because this is to the left. This is between 0 and that number. So in here is the negative 1.0434. So it's basically in that fail to reject region. So FTR, fail to reject, H0, and that was basically that this was bigger than or that we can't reject the possibility that mu1 is greater than or equal to mu2. Okay, there's a possibility that they are equal, so we cannot support the claim. There's insufficient evidence to support that claim at the alpha 0.05 level. Okay, so we're going to stop there. So those are the means between independent data, and then I'm going to pick this back up in another video with difference of two means and paired data. So we'll just pick this back up and I'll see you then.